make sure that I'm still streaming here, so it's working out. So we got most of the way through this on our first day of class, and we are here to pick up on the pep talk portion. What can MLM do for you? So I'm in lecture 1 on slide 12. That's where I'd like to kick things off. Okay, can you all see my screen?
Mm-hmm.
Yes.
Yep. Okay, excellent. So what can MLM do for you? We'll go over each of these points in turn. Modeling dependency, including all kinds of predictors, handling messy data, and keeping in mind that it's not that far away from models that you already know. So first up, model dependency. So the phrase dependency, it sounds like something bad, right? Like you talk about violations of independence or dependency being something that you have to fix or handle or address. Dependency just means correlation. That's what it means. It means that observations from the same something are going to be more alike than observations from different somethings. So that could be people who go to the same school. It could be occasions from the same person. And so forth. So dependency is a negative term for what is really just correlation. And there's different types of sampling designs that you can expect correlation or dependency for. And we will hopefully get a chance to have examples of all of these. So the term dependency is often associated with level. So in these models, we talked about there being 2 levels. Level 1 is time. Level 2 is person. And so that's another way of thinking about there's 2 dimensions of sampling. There's differences across occasions or change over time or variation over time, as well as differences across people. So we would say that there's at least 2 kinds of variance and 1 kind of dependency, meaning we need at least 2 levels. We need the regular type of variance and then plus something else for the dependency. So we have sampling dimensions that can be nested, and nested is a term that gets used in a whole bunch of different ways, but what I mean here is just that the units belong to a higher order organization. So occasions within persons, occasions within groups, so if you have, say, a longitudinal study of countries or something like that, experimental trials within the same person or subject. Sometimes nesting is easy to think about, and sometimes it's more complicated. And if you're ever thinking about a sampling design in which you can't figure out which way the nesting goes, what's nested and what, odds are good it's not nested, it's crossed. So for instance, if I have some sort of round robin design where I rate everybody else in my class and they in turn rate everybody else, then that is a cross design where we would say that the target, the object of the rating, and the rater themselves are crossed random effects. Same thing if we have an experimental design where people all respond to the same items, then people and items are crossed as well. And so in those cases, the same logic applies. Responses from the same unit are more likely to be correlated. So responses that belong to the same item are responses that come from the same person. One thing to keep in mind in thinking about dependency is that there has to be additional variation after controlling for the model's fixed effects. And so this is a point of confusion frequently in thinking about intervention type studies where people might be assigned to groups. So let's say that I have a longitudinal intervention. I have 1 treatment group and 1 control group. And after I put into the model a predictor of which group you're in, there's no more variation related to group. It's saturated. So even though people are nested in groups, group is not a level. There's no additional dependency related to group. When there would be dependency is if you have multiple groups of each kind. So let's say that I have intact groups, like I'm studying something like existing people getting some kind of therapy. And I might have 10 therapy groups and I might have 10 control groups. In that case, group is another level. There is additional dependency related to group even after you put in the model, whether it's control or treatment, because there's still going to be differences among the 10 control groups and among the 10 treatment groups. So that's an instance in which group is a level, because there's that extra variability that that single fixed effect, that single dummy code for control versus treatment doesn't account for. So I can't see anybody's faces. I'm talking to myself. How are we doing so far? Good? Good? Okay. Questions?
Yeah.
No? Okay. All right. I'll keep going then. So in longitudinal data, there are probably at least three, but these are the three main sources of dependency that we're going to be figuring out how to model, how to represent in the context of a model. The first one is the one that's the most obvious, and it's the one that people think about in a predominant way when you think about dependency, and it's the idea of mean differences. So if I have an intervention study trying to improve someone's health, for instance, some people are just healthier than others. That has nothing to do with me or what I'm doing in my intervention. They just walk in the door that way. And so to the extent that some people just have a different mean of the outcome over time, that's one kind of dependency. And it's a constant kind of dependency because it's going to represent the same level of correlation across all of the occasions. And we're going to address that in our models with something that's called a random intercept. Second on the list is another kind of dependency, but it's a predictor-specific kind of dependency, and it's individual differences in the effect of time-varying predictors. So to the extent that a predictor affects people differently, so it could be time itself, to the extent that people grow at different rates, to the extent that if you have within-person differences in stress, to the extent that that stress affects a person differently than a different person, that's another kind of dependency, but it's specific to their variation on stress or their variation on time. And those kinds of sources of dependency will be represented by random slopes that tie to those predictors that have the dependency. Whether or not that's present in your data is an empirical question, answerable by a specific type of test. And then last but not least, there is the catch-all phrase. I don't have a more eloquent description for this, but it's non-constant within-person correlation for unknown reasons. It's just the idea that the closer in time you are, the more related you are. What happened yesterday is likely going to be correlated with what happens today, and today is going to be correlated with tomorrow. So people have more similar outcomes for occasions that are closer together in time. And in that case, you're just trying to make a good guess as to what the pattern is for the relationship, how quickly the relationship decays over time, and there's different types of autocorrelation patterns available for this. So we will learn techniques to build each of these kinds of dependency into the model, 1, 2, or perhaps even all three. It just depends on the type of design that you have and the type of phenomenon that you're studying. So why do we care? I'm pretty sure no one has ever woken up in the morning and said, you know, I really wonder what kind of dependency my longitudinal data have. No one's ever said that. The reason that we have to care, though, is so that we can get the right tests of the things that we do care about. In other words, when we put predictors into a model, the standard error for those predictors comes from the model for the variance, meaning it comes from how many different kinds of variation we've introduced into the model. So if we have variation over time and over persons, that's at least 2 kinds of error. If we pretend that we only have 1 kind of error, then the standard errors can't be right, and if the standard errors aren't right, the p-values aren't right. And depending on how you've screwed up, the p-values can be too lenient or too conservative for different types of predictors. So it's the inference about the predictor that matters from whether or not we've come up with a decent way of modeling whatever dependency is there. The other reason why we should care about dependency is that it provides a roadmap. So the sources of variation that exist is going to then dictate what kinds of predictors are going to be most useful. So if we have a data set that's longitudinal, but it turns out that people don't really change that much, if there's really just a lot of between-person variation as opposed to across-time variation, then the only way that we're going to be able to predict that between-person outcome variation is with between-person predictors. Likewise, if it's mostly variation over time, we need time varying or time specific predictors. So knowing how much variation we have related to each source, how much dependency we have related to each source, is going to then dictate which predictors are going to be most helpful. Okay, and then in terms of the predictors, you can have any kind of predictors in these models that you want. There's a language that is taught in introductory level statistics that I find is really unhelpful. The idea that you need different labels for different models depending on what kind of predictors you have. So for instance, at some universities, your first year sequence would consist of one class on regression and one class on ANOVA, where ANOVA would be all about putting predictors in models where the predictors are discrete grouping variables. Regression would be about putting predictors that are supposed to be continuous, for which you would have some kind of slope. That's an arbitrary distinction. What if you want to fit a model where you have both kinds? There's no problem with that. The only problem with that in the context of repeated measures is that if you have a predictor that's assessed repeatedly but isn't a grouping variable, repeated measures ANOVA is not designed to handle that. And so that really is where multi-level models that we're going to learn shine. It's the analog of basically repeated measures regression as opposed to repeated measures ANOVA. And in longitudinal studies, we'll have predictors that are measured at different levels. So some things don't change over time. The characteristics that a person has when they walk in the door, those are known as time invariant predictors. Things that do change over time, things that you've measured at each occasion, those are time varying predictors. Some things might be measured at higher levels. So let's say that you're doing a longitudinal study of relationship satisfaction among people who are together in a relationship. Well, you might have variables measured for each person over time, but you also might have couple level variables, like how long they've been a couple, or how long they've been married, or how long they've been parents, or something like that. So you can incorporate predictors at any level of analysis, as well as interactions between levels. So you're limited only by your own creativity. There's no difference in the models in terms of what they would be called as a function of what type of predictor you put it. Okay, with me?
Yes.
Yes? Any questions, folks? Nobody wants to ask questions?
I guess I can ask one.
Sure, please do.
Are we differentiating between fixed and random effects here when we talk about predictors, or are they kind of referring to the same thing?
Most of what I'm saying pertains to fixed effects. However, random effects you could think of the same way. You can have random effects of any kind of predictor. The only catch is that you would have to have a higher level of sampling for it to be random over. So for instance, in two-level models where occasions at level 1 are nested within persons at level 2, time invariant predictors are level 2 predictors. Those can only have fixed effects. They can't have random effects because there's no level 3 for their effects to be random over. So yeah, you can have fixed effects at the same level. You can only have random effects at a higher level. So we'll get to fixed versus random in I think 1 or 2 lectures from here. So.
Okay.
So other questions? Thank you for talking. It's so weird to just be sitting here in my basement talking to my laptop. But it's better than freezing to death, so there's that.
Yeah.
All right, so next up, the single biggest selling point for why these models are useful. Because people don't cooperate. So when people say things like repeated measures ANOVA, what they are probably referring to is not just the model itself, but a specific way of estimating it, which is using least squares. And that's all the stuff that you were taught and probably had to memorize about sums of squares and expected squares and f-tests and all that stuff, right? It's the kind of analysis that one can do by hand. Unfortunately, that kind of analysis that one can do by hand is only appropriate for a very, very limited type of data. So if we were to do that type of traditional analysis for longitudinal data, on my screen here on slide 17, on the left-hand side, let me see if I can do my mouse here, that will help. Let's go pen. No, here's my little red pen. So the type of data structure one would typically use for repeated measures analysis is where the repeated observations are defined by different columns. So for instance, here's my outcome at time 1, time 2, time 3, time 4. And the data structure is such that people have one row. So it's one row per person. So what happens then in this type of analysis to person 101? And feel free to read from the screen.
Excluded.
They're excluded, list-wise deletion, because the rule is the entire row has to be complete in order for us to be able to compute sums of squares, mean squares, f's, and so forth. We can't interpolate data. But that's really not fair, right? Person 101 stuck it out for 3 out of the 4 occasions, and you're telling me that I can't use those? Not cool. So the way that these models solve the problem, in addition to changing to a different type of estimation that involves likelihood, is also by reconceptualizing the data structure. So this is something that I asked you to do in your Making Friends with SAS homework. And this is the slide that I was hoping to show when my computer locked up last week. But this type of data structure on the left is what's known as, I call it multivariate. It's also known as wide. We're going to take this data structure and transform it into what is known as stacked or long. And here, it's one row per occasion per person. So any variable that is time invariant, that is level 2, that is a person level piece of information, such as ID, such as their gender in this case, gets pasted down across all the rows for a person. The other information that used to be there then requires 2 columns. Y then is what I've named my outcome generically, and as you can see, each row takes a value from a different column. So time 1 goes into row 1, time 2 goes into row 2, and so on. Then the names of the columns, then that information has to be created in its own column instead, where I have time 1, 2, 3, 4. So in this data structure, the rule is the same. Only rows that are complete get used. The difference is in the definition of what a row is. So now, person 101 is going to have their data from time 1, 2, and 4 included because those rows are complete. Their data from time 3 is not going to be included because that row is incomplete. So it's the same rule. It's just that it's per occasion per person rather than per person. And so missing data are ubiquitous, but another way that people cannot cooperate is by not showing up exactly when they were supposed to. So if you have a study in which the timing of the observations is really important, you want to pay attention to exactly what occasions people came in on. So I have an example of this problem at the bottom of the slide here. What if somebody didn't come in exactly at time 1 and exactly at time 2? Let's say their third occasion was late, such that it was halfway between time 3 and time 4. It's actually time 3.5. Well, which column would I have put that in? Either way, I'm rounding. And rounding a variable is a way to introduce measurement error. It's no good. Because the information that used to be used to define the columns is now itself a column, that means that we can have any set of occasions that we want, and they can differ across persons. And so we are able to model change through whatever occasions a person has, even if each person has their own unique set of occasions. And so the term for this that I use is unbalanced. It's the idea that people are not on the same measurement schedule. So there's 3 different words that people get confused in thinking about this. One is incomplete, one is equal interval, and the other is unbalanced. So in looking at this example here, I would say that person 101's data is incomplete, but that it's balanced in that I still have the same 1, 2, 3, 4 possible occasions. If I were to sub in the occasions from the person at the bottom of the slide here, I would say their data are complete because they have 4 occasions, but they're unbalanced in that they're on a different measurement schedule. They are further unequal interval because the distance between them is not the same. So in your Making Friends with SAS homework, I had asked you to compute 2 different time variables for this reason. One of them, I think I asked you to call occasion or wave or something like that, which is just an ordinal index of which occasion it is. But then we also need a more specific version, such as years in study, months in study, something like that, that keeps track of not only, hey, come back, exactly when people were measured, but the distances between them, a non-rounded version of time. So that will be important to put in the model itself so that we're not artificially creating measurement error in a predictor variable of time. So, does that make sense? Questions?
So one question that I had was,
Sure.
when I think Michelle already stated this and you finished that on the first class, since I was able to watch the YouTube video that you posted, was study designs only have 2 time points. So for like pre and post. So if we are doing it in a stacked long structure and we're missing, say, the post, I mean, what is the pre-data from that participant actually giving us in terms of utility uh, in that case? Like, is it showing us how much variance can exist in the subject population, since we really can't look at like a change over time um, in those participants?
Yeah, so there's 2 things that keeping that type of incomplete data in would accomplish. One is that whatever data you have at pretest contributes to having a better estimate of your outcome and effect of any predictors at pretest specifically. So if you think of it as pretest being the intercept, for instance, your intercept is better represented by more data than less data. With respect to post-test, the difference is attributable to the assumptions of missing data that underlie the use of either least squares versus likelihood. So least squares assume something called missing completely at random, which is exactly what it sounds like, that there's no reason why certain people didn't come back whatsoever. The assumption that underlies likelihood estimation is missing at random, which means it's random once you control for the reasons of missingness that are available in the data. So to the extent, for instance, that people who had a lower pretest score are more likely to drop out, then the model estimated post-test mean is going to not be the exact complete data mean, but it would be the mean that is expected based on someone's pretest score. So it's supposed to give you a more realistic version. What the model is trying to do is come up with what the means would have been at each occasion had the data been complete. And so it's supposed to be a more valid estimate to the extent that the reasons for missingness are available in your data set. Now, if there's something about people who were more likely to drop out and it's not because of pretest, then you're on your own. That's the case of missing not at random, in which you really can't do anything about it other than make some assumptions and try to guess. But it's supposed to be better to use whatever data you do have. And these models do also allow covariates for missingness. So if you know that certain people are more likely to drop out, those reasons can become predictors in the model to give you a better estimate of what the ending point would have been, even if they had missing data. Does that help?
Yeah.
Okay.
So does that mean is it wrong to think of it as some type of imputation?
Yeah, it is.
Yeah.
Imputation is asymptotically the same as likelihood, so long as the same things that go into your imputation model would go into your analysis model in a likelihood estimation. You're not actually filling in the values. This is where I'm trying to use my hands and it's not helping. Like if you picture a mountain, right? Like if you have a bunch of like rocks in the mountain and you're trying to sketch the mountain around them, the idea is that if you take any one rock out, the shape of the mountain shouldn't change. And so if the rocks that you're removing would change the shape of the mountain, that's bad. The idea of missing at random is that you have your mountain, but the shape of it is still intact, even if certain rocks are missing.
Okay.
So it's not filling in the rocks. It's just trying to recover the overall shape. And in this case, it's a multidimensional likelihood function. And I think of it as a mountain in my head, which is what I'm trying to use my hands to draw, even though no one can see me. So it's just trying to recover the right shape. Filling in the data is one way to try to do that. The other way to try to do that is just to try and estimate the person's likelihood and hope that the things that are missing wouldn't have changed the shape.
Okay. All right, thank you.
Sure. Who else wants to talk? Radio silence. Are we still there?
Yes.
Okay, thank you, Ori. Is anyone else still there?
Yes.
You know, there's an option on here where I could have it beat me if your screen gets minimized, right? You know that. It's the spyware option that all the training videos for human resources use. They automatically stop if you move away from the little video. But no, I haven't invoked that. But I'm missing the feedback online, so please do let me know if there's things you want to talk about. So last but not least, this is my pep talk for the fact that you know how to do most of this. You know the same concepts that underlie these models. So what's an intercept? Who remembers what an intercept is? You would have first learned this in like 8th grade algebra. You would have learned it in a regression class. It's the same thing. I'll start you off with your sentence. Expected outcome when
all x's are 0.
Yes, when all x's are 0. Guess what? That's still what an intercept is going to be for us too. And this when all x's are 0, we're going to make sure that 0 is a meaningful value within the scale of all of our x's, of all of our predictors, so that the intercept stays meaningful. Very good. The effect of a continuous variable, like if I told you that my slope is 2, would someone like to put 2 in a sentence?
Expected change in predicted score for the independent variable when 1 unit increase or decrease in the continuous variable.
Yep. It's the expected change in y for a 1 unit change in x. Yep. If I gave you a slope for a demicode, for instance.
That's gonna change the way that we write the equation, prediction equation, like 0 for males, 1 for females.
Yep. And then the slope is the group difference, right?
Yes, group difference.
Yep. Same thing. And then last but not least, a variance component, or what I'm going to refer to as a pile of variance. What's variance?
I don't want to say the formula.
No, I'm not looking for a formula.
The
Residual.
standardized change between the groups, let's say. I mean, with the data available.
Let's say that your grandma wants to know what you do for a living. This happens to me, right? So what is it you do again? Try and explain variance to your grandma.
Oh my god. I will say I'm working at the coffee shop instead of explaining variance.
Yeah, well, my parents just tell people I teach college. And then when they ask for details, that's where it gets a little tricky.
Yeah.
But yeah, variance, right? Well, that's a stats term, but the idea of variability, you know, that people are different. Things are different. How different are they? Well, on average, they're this different. That's what's known as a standard deviation.
Yes.
So we're going to take that idea and we're going to augment it to cover different kinds of differences. So for instance, if we sample people longitudinally, we know that people differ from each other already. Even in a cross-sectional study at time 1, they differ from each other. But then they're going to differ from each other in how they change over time. So that's another kind of variability in people's rates of change. There's also the fact that one day is not the same as the next day. There's differences across time, and some of that is related to how they change, but some of that's just other time-specific reasons. So that's another kind of variance. So the big catch in these models is trying to figure out how many kinds of variance we have, and then what type of information is related to each kind. So it's a big regression-a-palooza, but the underlying elements are the same as what you already know, intercepts and slopes. So here's the list then of everything that we're going to be hoping to tackle this semester. First off, because I had to pick some software to demonstrate things in, I'm picking SAS, and I want everybody to at least be familiar with how to get data in, how to make variables. It would be a really good activity for your homework if you could do your homework in one language and figure out how to translate it into another language that you're more likely to use in the future. So if you get everything right with SAS, for instance, then you can go back into R and try and make it work with Elmer, or SPSS, or Stata Mixed. M+ is the one that you wouldn't be able to do if we're using a certain kind of likelihood estimation known as residual likelihood, because it doesn't have it, but otherwise different packages would be able. So it's helpful, I think, to help the concepts sink in if you can do it in more than one language. What we're doing with the rest of today and Thursday is reviewing single level models. So just regression, just making sure that we have the same terminology as a basis for moving forward. Then we'll hit within-person analysis and kinds of ANOVAs, moving on to describing how to model patterns of within-person correlation over time in data where the focus is fluctuation. Then moving on to data where the focus is change and how to talk about different types of linear and nonlinear change. Then we'll stop by reviewing interaction terms and just single level models again, because when we get into predictors with longitudinal models, you'll quickly find that almost every term becomes an interaction of some kind. So it's really important that we get interaction terms under our belt before making them more complicated as longitudinal. And then the last topic that I'm hoping to get to is how these models are used in repeated measures experiments. So cross designs, for instance, where people respond to the same items and that kind of thing. At my previous jobs, I was able to teach an advanced course that talked about time-varying predictors and multivariate models and how to put all of that together. We'll see in the future if I'm able to do that here, but if not, the course that covers that the number is 945. At both of my universities, I was able to have that number, so it's on my website if you want to see any of that stuff. So that's that. So are we still pumped?
Woohoo!
Woohoo!
Yep.
We're here. Anyone else pumped? Pumped is a good thing. Shameless plug for enthusiasm.
I'm still
We're pumped. All right. Well, let's do some reviewing.